Hi everyone, today is Tanya speaking. Now I'm presenting this paper, GPU accelerate graph label propagation for real-time float detection to you. First, I will make a short introduction on the authors. I'm a PhD candidate from Singapore Management University. Professor Li, my supervisor, is also from SMU. Professor He is from National University of Singapore. Zhao Li is from Alibaba Group, and Professor Sun is from Zhejiang University. As we all know, a graph is a arithmetical structure that consists of set of nodes and edges connecting certain pairs of them. Many real-world data can be naturally presented as graphs, and therefore graph algorithm has been adopted to solve many types of graph in real-world problems, such as finding the shortest path from one place to another, ranking the importance of a website by searching agents, decide how to assign different jobs to each agent in bigger company. Our paper focused on a fraud detection problem online shopping network. Today, financial companies urge to efficiently detect anonymous behavior of their users. In Taobao, a famous online shopping platform in China, where billions of customers seeking goods through their website every year, research suggests that 1/3 of those customers will check the ranking and reviews before they decide to buy. As a result, many online shops choose to hire a group of fake customers to raise their radio ratings, which block the fairness of the platform. Here we introduced a fraud detection pipeline of Taobao. We have proposed data as the input of the detection process. The data contains two parts. One is the transaction logs, and the other is a pool of blacklist IDs, with which we can control the graph. The detection process starts with a label propagation algorithm to identify all suspicious causes in the network. The identified suspicious clauses are sent to the downstream analytic text, such as graph neural nets for further identifying new flaws. On Taobao's platform, the label propagation and its failures works as a core component of the whole process, which have very time-consuming. This component can operate more than 65% of the entire pipeline due to the large space and the complexity of the network. This huge overhead makes real-time analytics hard to work in practice. In the meanwhile, real-time fraud detection is a pricing challenge today. More than 20% of the traffic to e-commerce portals are malicious robot in 2018. Thus, it is critical to speed up the label propagation bottleneck in the pipeline. Here we give an illustration of how the classical label propagation works. At first, we assign each node with a unique label represented by different colors in the figure. Then iteratively, each node propagates its current label to its neighbors. Then after this, all label as the most frequent label it has received. After some iterations, labels are going to converge, and the node with the same label will classify to the same clusters. Recently, there's a rapid growing interest in employing a GPU to accelerate various graph processing workloads, such as the graph traversal, page rank, and network motif detection. Those existing was leverage the associative process properties of their attacked applications to efficiently distribute their workloads. However, for each iteration of the label propagation, every node scans their labels for the label and select the most frequent label. Note that identification for the most frequent label is not associative workloads for each label list, which resembles most existing study infeasible for accelerate label propagation efficiently. For instance, suppose we have a list of we have a list at the bottom of the slide. If we divide it into 3 parts and we found the most frequent fatal individually. For the first part, B is the most frequent. For the second part, C is the most frequent, and for the third part, D is most frequent. But when you investigate the entire list, A is the most frequent label. Thus, it's hard to directly distribute the workload for the parallel computation. Now here we see the two major challenges when we deploy GPUs to accelerate the label propagation process. Finance companies like Taobao use the various label propagation algorithm for different application requirements, which rests demands of user-defined, efficient, and scalable label propagation algorithm. Besides, exciting words simply leverage the real computation power and high memory bandwidth of the GPU, which are not optimal. Here we give an overview of our system. We use the two structure a graph and attributes to represent the underlying graph and its attributes or labels. The compressed spaced log format is used to store the graph structure. The use of our system can include additional user-defined data structure for customization. The workload of our system is iterative, and each iteration contains 3 main components. The first component is a pick label, which is responsible for defining a label for each node according to the user-defined strategy. The second component is label propagation. Each node will pick up a label which achieves the highest score value among the neighboring nodes based on user-defined score function. The last component is update vertex, which is responsible for updating strategies of labels which with user-defined strategy. We provide an API to help developers to customize and deploy their label propagation algorithm on GPU for different application requirements on the data size pipeline. We show some of sample APIs on the right-hand side. Now we introduce the exciting words deploy GPUs to accelerate GPU label propagation process. There are 2 categories of those methods. One is the hash table based method on the left-hand side, and the other is the sorting based approach, which result the label list by their labels on the right-hand side. However, neither hash table based approach nor the sorting based approach for utilize the GPU resources. For the hash table based approach, if the label list size is larger than the shared memory size, GPU has to access data from slow speed global memory. And if the label list is too small, many threads will be remain idle because the workload shortages. For the sorting-based approach is deploy a segment sort approach, which require multiple scans on the label list. Additionally, when the set of label list is large, this approach serves a clean performance degradation for long-distance memory swap between warps and even blocks. We propose optimization to maximize the shared memory usage, even if the label list does not fit into the shared memory. This is based on important optimization. 2 labels of vertices often share the same label when they have a high chance to be in the same community. However, directly set the size of the hash table less than the size of the label list is unfeasible because we fail to count all the labels. We compare a hash table and a common sketch to solve this problem. Suppose we have a high degree node on the left-hand side, which label list cannot fit into the shared memory. The key sort hash table is responsible for keeping the accurate count for the key distinct labels, and the count for the rest of the labels will be estimated through the common sketch, which offers an upper bound of the accurate count. Since we only need to identify the most frequent label, we can simply bound up most of the labels by this sketch. Here we give an illustration of how we combine these two structures together in detail. Suppose the hash table size is 5 and the common sketch contains 3 5-sort hash table which with independent hash functions. In the early stage of the insertion, hash table is not full. We can continuously insert the new labels into the hash table. If the number of distinct labels exceed the complexity of the hash table, we insert the label into the common sketch instead, and in the meantime, we record the accurate count of those labels in the shared memory, in the global memory. The common sketch records the total count of all labels that are inserted into the same sort by different hash functions. Thus, it provides a good upper bound for the accurate label counts. If the maximum label count in the shared hash table exceed the maximum count estimated by the common sketch, we can confirm that the most frequent table of the label list is the label with the highest count in the shared memory hash table. Otherwise, we revise the tables whose estimated count exceed the maximum count in the shared memory from the global memory hash table. In the example, most frequent label kept in the hash table is A with the count of 3, and the label D and F that are estimated by the common sketch have a less count compared to A. Thus, we can ensure that A is the most frequent label within the label list. Here we introduce another optimization that maximizes the workload for low-degree nodes. Unlike the former nodes, which assign one warp or threads to each node, we assign threads in a way that most threads in the warp are active. For example, suppose the warp size is 10 and the degree of the first 3 nodes is 2, 3, 4 respectively. Only one warp is responsible for handle the neighboring list of all those 3 nodes simultaneously. In order to schedule threads representing the different nodes and labels, we kept a mask in each threads to indicate whether the threads that can operate at the colonel stage. We also adopt warp level interests that spot a bit of manipulation to accumulate the actual count for each label, which is much more efficient than atomic operations. The left-hand side is the table summarizing the data set that we use to compare our approaches with the state-of-art approaches. The compared method and the single machine settings are listed on the right-hand side. We evaluate overall performance of all those methods over different label propagation algorithms. Classical label propagation, layered label propagation, and the speaker and the listener label propagation. We run 20 iterations for each algorithm and benchmark the solutions by comparing their speed up of OpenMP solution. In particular, GLP, our system achieved 4.5 and 7 speed up over GSOT and GHash on average, respectively. For the other two label propaggation algorithm, the results are consistent with those of the classical label propagation. In summary, the results have demonstrated that the GLP significantly outperform the state-of-the-art solution of both the CPU and the GPUs. Furthermore, the API provided in the GLP allow data engineers to quickly develop a customized label propagation algorithm without domain knowledge of the GPUs. We demonstrate the effectiveness of our proposed optimization by activating our optimizations one by one and report the speed up of the approach, which use a global hash table for label counting, and the result provide the effectiveness of our optimizations. We start a real-world dataset pipeline to further demonstrate the strength of our system. The pipeline maintain a sliding window containing the transaction in the past 10 to 100 days. A graph is constructed for each sliding windows connecting the details of in the transaction. The graph size of the different sliding window configuration represent the top in the top table. We compare our proposed GLP with the current in-house distributed solution used in Taobao, which use a cluster of 22 machines, where each machine is equipped with 4 high-end CPUs, whereas our system running a single machine settings the same as the formal experiments. We run a label propagation algorithm for 20 iterations on the real graph workloads and report every running time for one iteration. The experiments show that GLP achieves 8.2 speed up on average against the current in-house distributed solution used in Taobao. To verification the effectiveness of our system on a multiple GPU settings, we add one more Titan-free GPU to the original setting. GLP further achieves 1.8 speed up on average. The CPUs used in each machines of the in-house solution cost more than $20,000, whereas the CPU GPU setting used less than $4,000, according to the official price from Intel and NVIDIA. Because GLP can also provide greater mining savings with one machine to handle the current Intel workload efficiently. At last, we summarize our work as follows. Thanks for listening.